This is an illustration given in Thompson that helps us visualize what's going on when the computer selects different predictors for entry into a regression equation. And it more specifically illustrates why the computer cannot analyze all sets of predictors and give us the best set to explain the most variance in the DV. So here we have a 4 predictor case, and I have doctored up this illustration with some colors so that it's easier to see. We have a DV that is illustrated as the red box, so that's our Y variable. And then we have these other predictors around it and explaining variance in it. And it's kind of like a Venn diagram, but without circles, it's squares this time. So we have our x1 variable, which is noted as the blue square. We have the x2 variable as the yellow rectangle, and the x3 is the green rectangle, and x4 is the purple one. And so you can see that they share variance with the DV to varying degrees. And just as a hypothetical example, Thompson gives each of these R squares different values. So for example, for for x1's correlation with the DV, it is R squared of 0.25, and this is all noted beneath the slides. You can take a look. The predictor 2's shared variance with the DV is 0.2. Predictor 3's shared variance with the DV is 0.2275. So that's 22.75% of the variance. And then predictor 4 is 24.75% of the variance. So basically what we have here is a situation where if the computer is going to select the first predictor to go into the equation, it's going to select x1 because that has the highest bivariate with the DV. So that is 0.25. It explains the most variance of all of them. Note that x4 is almost there. It's 0.2475. But it just misses the cutoff because x1 is slightly bigger. So what that does is it throws the whole thing off because next the computer is going to select the variable that has the next highest percent of unique variance accounted for, and that's going to be x2. As you can see, the yellow box is showing the most unique variance explained. And so it's going to select x2, and then after that it's probably going to stop because we have 0.25 plus 0.2 is 0.45. So 45% of the variance explained. And that is going, and we can't explain any significant more unique variance. x3 doesn't give us more unique variance, and x4 does not either. So the computer is going to stop at that point. But which 2 predictors explain the most variance together in the DV? Well, that happens to be predictors 3 and 4, which the computer has ignored. So if you take the bivariate, or the variance explained, I should say, for x3, that's 0.2275, and you add that to the variance explained by x4, that's 0.2475, and you get 47.5% of the variance explained. And so 47.5 beats 45%, not by much, but you can we could probably think of a scenario which it would be way different. So anyway, the whole point of this example is that when the computer selects the variables, it does not give us the best solution. And this example proves that, especially because it chose x1 first. That caused a cascading effect where we couldn't correct for it, and so we did not get the 2 that were most important in predicting in total the most variance explained in the DV. So I hope that makes sense and gives you like a concrete way to think about why Thompson's third rationale makes a lot of sense. So again, to my knowledge, there is no software program that analyzes all possible combinations of predictors and then selects the one that explains the most variance. Even in that case, it would probably not be ideal because, again, when we're exploring all possible combinations, we have type 1 error to deal with. So the computer program would not only have to analyze all those possible combinations and pick the best combo, but it would have to do so by adjusting for type 1 error as well. And again, currently, I do not know of a program that does that. So we're back to our original assertion, and that is that the researcher is the one who should decide the entry of predictors into a regression equation, always.